Everyone knows some things about the honeybee. Her industrious buzzing from flower to flower seeking nectar, the delicious product she makes from that nectar, and the potency of her last resort defense. Such things as are commonly known about the bee do not suggest a beehive as a good place for a lesson in mathematics. But here, as in all of nature, understanding what is happening involves mathematics. For mathematics is the language of science. This piece of honeycomb, a little over an ounce, represents over 20,000 bee miles for collection of nectar, the raw material, plus over 110,000 bee hours spent transforming the nectar into wax, to which must be added more than 18,000 bee hours for fashioning the wax into comb, according to a precise pattern. Since honeycomb is so expensive to construct, it's obvious that economy in the use of wax is very important to the welfare of the hive. Is there a geometric shape which is more economical to build than any other? We have made models in which each has the same volume and the same height. Which of these requires the least amount of material to build? That is, which has the smallest lateral surface area? Since the height is the same, the one with the shortest perimeter is the best. More sides mean less perimeter. Thinking of the cylinder as having an infinite number of sides shows that it uses the least material. But cylinders are only economical if they stand alone. Placed together, they leave large gaps between them. Since no walls can be shared, they are wasteful of both space and material. Wherever walls lie side by side, they can be shared by two cells. That is, one wall can do the work of two. Thus, octagons, in which 4 of 8 sides can be shared, save 25% on material. Triangles, by sharing all their sides, and squares, save 50% on material. Therefore, when we consider the savings possible through the sharing of sides, the material needed to construct cylinders does not change. But the other figures require less material, for they share sides. Of all the figures, the hexagon uses the least material. This is the shape the bees use. This discovery of the economy of honeycomb was made over 16 centuries ago by an Alexandrian geometer, Pappus. What he and others have learned about honeycomb has been applied to build the largest grain elevator in the world. The hexagon provided the most economical, the strongest design. Such study of living things is today called bionics. Much effort is being expended to learn from a wide variety of creatures, and results are coming in. Study of the eye of a beetle has resulted in a device installed on planes which measures their ground speed more accurately than had been possible before. Study of the common housefly has given us a new, extremely rugged gyroscope. Indeed, there seems to be no area in which men cannot learn from the abilities and organs which God has given to his creatures. And in practically every instance, mathematical calculations are involved in understanding the animals and in applying what we learn. There is much more we can learn from honeycomb. A structural engineer can show us other advantages of the hexagon among all the patterns the bees might have used. When certain transparent plastics are placed in a polariscope and a stress applied, colored patterns appear. The series of rainbow changes are most numerous where the stress is most concentrated, as at the corner of the notch, the weakest point on the bar. The stress patterns from various geometric shapes are most revealing. What if bees had built square cells? One of the drawbacks of square cells is that a load along a partition is not readily transferred to adjacent partitions. In triangular cells, a load at any point is distributed to several members. However, there is a major drawback. The horizontal members are loaded in compression. This is the wrong way to load a thin plate, which readily buckles. In hexagonal cells, however, the load is distributed as a tension. This makes maximum use of the strength of the thin wax walls. The pattern is so strong that less material is needed in the walls to support the load. Bees take advantage of this and make the walls of the cells less than 3/1000 of an inch thick, thinner than a sheet of paper. It's amazing, isn't it? Bees build honeycomb just as if they were graduates from the best schools of engineering, using the shape which is not only the most economical, but also the strongest. The understanding of the polariscope pattern by an engineer requires a great deal of mathematics. In fact, to go into a thorough study of the structure of honeycomb involves mathematics so complex as to require a computer.